All right, let's see if we can solve this problem. This is gonna take a while, so please be patient. Let me start my timer. Good, so the problem we want to solve is we want to minimize with respect to x, negative sum for k from 1 to n, ak log 2, 1 plus gamma k xk with two constraints. A transposed x is equal to minus b, and let me give this a meaning. Let me call this p, which is some kind of total power. I'll also assume that all the a's are greater than 0, because if they're 0, you can remove them from the problem. They don't matter. And each xl is greater or equal than 0. So this is our original optimization problem. From this, we can compute the Lagrangian of x, lambda, and mu. And I changed a little bit the notation. So with mu, I will associate the Lagrange multipliers for each of the inequality constraints. So for all L, so this means that x1 is greater or equal than 0. And with this, we associate mu L, x2 greater or equal than 0, and so forth. And with each of these, we have one Lagrange multiplier. And with this equality constraint, we have a Lagrange multiplier lambda. So in the previous slides, I used lambda for the inequality constraints and mu's for the equality constraints. So here it's the opposite. I'm sorry for that, but it's more compatible with the next slides. Let's first make life a bit easier. Let's replace this log 2 with a log. It doesn't change the solution. So that makes life a little bit easier. Now this Lagrange multiplier is just the objective function. xk gamma k plus lambda a transpose x minus p minus sum k from 1 to n mu k xk. Now the solution must satisfy the following equations. So the derivative with respect to x should be 0, so this is a vector. Derivative of the Lagrange with respect to each xl should be 0. The derivative with respect to lambda should be 0. Mu L should be 0 for all, should be greater or equal than 0 for all L. XL should be greater or equal than 0 for all L. And XL mu L is equal to 0 for all L. For all L, yeah. Good. So then each of these conditions, we can now make it explicit. So let's take the derivative of the Lagrange with respect to one component XL. So then the summation, all of the terms will go away except the one corresponding to the alt term. So this gives me minus AL. Derivative of a logarithm is 1 over 1 plus XL gamma L times gamma L plus lambda, and then in this second term only AL will remain, AL, and then in the last term only mu L will remain. This should be equal to 0, so then I can put mu L to the other side and write it like this. This is true for all L. The second constraint just tells me that A transpose X is equal to P. So that's what this constraint tells me. And all the last ones, I cannot do anything with this, but now what's nice is that now I have an explicit expression for mu L, which I can use here and I can use here. So I just plug it in. So that means that I use it in the following way, that mu L is greater or equal than 0. That means that gamma L, no, lambda minus gamma L over 1 plus XL, gamma L is greater or equal than 0. That corresponds here for all L. Or equivalently, that this holds. Is that true? Yes, that's true. Then XL greater or equal than 0 for all L. And then XL, and now I plug in mu L from the first equation. Lambda minus gamma L over 1 plus XL gamma L is equal to 0 for all L. And now I've used up this first equation, so I can remove it. Good. We're almost there. So now what we find is that this last expression has two cases, right? Either XL is equal to 0 or lambda is equal to gamma L over 1 plus XL gamma L. One of these two has to be true. If XL is equal to 0, then the other constraint becomes that lambda is greater or equal than gamma L. On the other hand, if XL is not equal to 0, then we have this equation and we can solve for XL. And then it turns out that XL is 1 over gamma, 1 over lambda minus 1 over gamma L. So then we have these two expressions. We can bring those together, that XL is equal to the maximum of 1 over lambda minus 1 over gamma L and 0, with the additional constraint that A transpose X is equal to P. So this is our final solution, where the Lagrange multiplier lambda is set to make sure, that this equality constraints hold. And this is called the water filling solution. Okay, so it's a bit cumbersome to derive, but at least you have it here. I've also done it again, hopefully a bit cleaner on this slide. So objective function, Lagrange multiplier. These are the conditions, so derivatives with respect to each component in X with lambda, and these conditions on the mu. I can then solve for mu, plug it into the last equation, plug it in also in this equation. This gives me these additional conditions. In the end, there are two cases, either XL is equal to 0 or lambda is equal to this. This gives me the final expression of XL, where this 1 over lambda is make sure that we meet the total power constraint. So we choose this 1 over lambda to make sure that X transpose is equal to P. And the nice thing is that all of this is also valid when we replace all of these sums with integrals, right? With dx, or no, not dx, d gamma. Anyway, it also holds with integrals. Okay, this was a big effort, so let's see if this pays off. There are two cases. The one is called statistical water filling. The other one will be called deterministic water filling. We will see only for the discrete case. This means that the signal-to-noise ratio can only take on discrete values. The continuous case is more involved because it requires integrals. We will fix a target bit error rate and an average power, and we want to maximize our rate. So we want to allocate power and modulation formats to maximize our rate. We will specifically focus on mQAM in this case. And for mQAM, we have this expression that relates the bit error rate to the modulation format as well as the power allocation. So given a certain bit error rate, so we set this equal to, okay, some value that we want. We set this equal to equality. Then we can solve for the modulation format as a function of the SNR. So this expression in the middle tells us that if we've chosen a certain power allocation P of gamma, and then we have a certain SNR gamma, then this is the modulation format that we should choose with this many points. Now here, the M is continuous. So in principle, this could lead to modulation formats with like 3.6 points. We will deal with that later. And the value of K you can also find here from this expression. Okay, so now we know, given a certain power allocation policy, what is the modulation format for that SNR. So once we've solved the power allocation, we've automatically solved the modulation format allocation. And now we can formulate an optimization problem of this form where we maximize the total rate. So for each SNR, and the SNR can only take on discrete values, so the SNR, instead of a continuous distribution, is now some kind of discrete distribution, taking values gamma 1, gamma 2 till gamma L with some probabilities. If the channel has a certain SNR gamma L, then we will have a certain rate, log 2, 1 plus the signal to noise ratio. No, that's not true, sorry. This here is actually M of gamma. So when we have a certain gamma L, we will use a certain number of constellation points, which then leads to a certain rate, log 2 of M. Right, so if M is 8, we will send 3 bits using this SNR. We have a total power constraint. So on average, you cannot spend more than your average power. So it's not a total power constraint, it's an average power constraint. And all of the power should be non-negative. And this is exactly of this form that we've seen before with this matching. Right, so the A's that we had before are now these probabilities. The X's that we had before are powers. The C value is 1. Okay, the C was actually this constant here. We didn't consider this. And then these B values, they correspond here, these values there. So we can then apply the standard technique and find the water filling solution, which is this one here. So this is the water filling solution, which tells us that the power we should allocate is given by this expression above a cutoff value and 0 below a cutoff value. And this cutoff value is chosen such that the sum for L from 1 to L, P of gamma L times P of gamma L is equal to the average power. So this is to make sure you meet the average power constraint. And then it follows immediately. You can plug this expression for the power into here and solve for M, and then you find the results for M. So this tells you how big of a constellation should you use for this signal to noise ratio. So all of this is fine. The only problem that we have now is that this M is continuous, right? There is an extension to this water filling problem when the SNR can take on continuous values. So then we have an integral over all possible SNRs rather than a sum. But the nice thing is the solution has exactly the same form. So the power allocation is again of exactly the same form. The modulation format is exactly of the same form. And where this cutoff value is selected to meet the average power constraint. So now we go to this interpretation. Why is it called water filling? So the solution to the problem gives this power allocation. So the power allocated when the SNR is gamma is average power over a constant times 1 over a cutoff value minus 1 over gamma, above some cutoff value and 0 otherwise. So we now visualize this. On the x-axis is the signal to noise ratio of the channel, good or bad. On the y-axis is this function p bar over k times 1 over k. So this is just, no, sorry, that's not true. On the y-axis is p of gamma. Okay, and then we have this horizontal line here, which corresponds to this value. So this relates to the cutoff value. On the, okay, well, let me, I think this is not good. Sorry. X-axis, signal to noise ratio, and then I have this curve here, which is the power allocation. Which is this part, so p over k times 1 over gamma. That's this function. Good. There's a certain cutoff value gamma k here, and then if I evaluate this function, I get this value on the left side. Okay, so I evaluate this function. Sorry. I evaluate this function in gamma equal to gamma k, then I get this value here. I draw a horizontal line. Okay, I think I should take a break.